My experience as a teacher is that students often have difficulties correctly recalling these logarithmic formulas. Instead of memorizing, it's much better to internalize things, that is, to memorize something that we thoroughly understand. This video intends to give students strategies as to how to quickly and easily recall these logarithmic formulas. So let's see. So here's the bad news. You have to know this one. No matter which identity you're going to need, we will always derive them all from this one. So this one, there is no way around it. You have to be able to state it as I stated. And the good news is everything else derives from it. There's other good news. This is not so difficult. Suppose you're not quite sure, maybe you should have multiplied here, added there, or something like that. The first thing you can think of is, well, how about the question we know the answer? So we go back to our good old friend, log2 of 8 and log2 of 4. Now, we know what those things are, right? This is 3, this is 2. We know that's 5, and now we want to write 5 as a log2 of something. Well, that's not going to be 12, right? You can probably figure out that 32 is 2 to the 5th power. We're counting factors. So this here is the number of 2 factors you need for 8. Those are factors, so we multiply them together. And this counts all the 2 factors that we need to multiply together, so we get the 4. And then you let them into one group multiplying each other. That's not 8 plus 4, that is 8 times 4. Basically, you're allowing this group to meet this group. How many 2's? Well, 2 here, 3 there, so altogether 5, but this number here is 32. I think this specific example might be convincing. Let's try one more time. This is the rule. Really, what is going on? This statement here is just a restatement of this. It's not stated here in the way it usually is stated. Usually we start with a to the n times a to the m plus a to the n plus m. Now we go the other way around. First we say a to the n plus m. So in this second line, what is n? N is an exponent over a. M is an exponent over a. So when you multiply those two groups, how many a factors do you have? N plus m many. But somehow things are turned around here. Given that we know what n is, and given that we know what m is, what do we get when we use the exponent n plus m? Right, that would be this and that. So these are exponents. We're counting factors. And so the factors that are needed to this and the factors that are needed for that, when you allow them to meet, they're going to multiply each other. So either way, I hope you're going to be able to correctly recall the power rule. Suppose you need one of the logarithmic rules and you're not quite sure how to recall. It doesn't matter which formula you want to recall, I would start with this first one. So suppose you need to recall a logarithmic rule, not this one. But I just told you to start with this one either way. So how can we get the next one from it? One additional property has to do with inverse operations. What's the inverse operation of addition? What's the inverse operation of multiplication? So if we just rewrite the same statement with the inverse operations, so log a of b, instead of addition, we use subtraction. And then on the other side, instead of multiplication, we use division. That's it. Suppose you need another rule of logarithms. Still, go back to the first one. You can easily recall that by applying this rule repeatedly on the same quantity. So log a of b plus log a of b is log a of b squared on one side and 2 log a of b on the other side. And then this can be repeated 3 times, 4 times, n times. What happens if we repeat this n times? In the middle, we're going to have log a of b plus log a of b n times. There are 2 different ways of simplifying that. Either we can say, well, if you just add the same quantity to itself, we have multiplication notation for that. So that's the same as n times log a of b. And on the other side, applying our basic rule, basic property of exponents, it's log a of b to the n. And if you ignore the middle and you just look at the ends, that is our rule. We just derived it. N times log a of b is the same as log a of b to the n. This is not a proof, because in this argument n has to be a positive integer, and this rule is true more general for any real number in the exponent. However, remember that we're not trying to prove it, we're trying to recall it. Eventually, you don't even have to write this down, but you can just close your eyes and see that repeated addition and sort out what the formula is. There is just one more formula left, and for that, I would actually derive it. If you go back to that video, you will see that that formula was derived 4 times in that video, and there was a reason for that. In my own student years, every time I needed the change-based formula and I wasn't 100% sure of it, I just derived it. And you don't have to use letters or variables that you don't like. You can use specific examples that you're comfortable with. We did log 3 of 7. Remember log 3 of 7, we made it x. We rephrased the logarithmic expression into an exponential one. 3 to the x is 7. And now we took any logarithm of two sides. I'm going to take, well, log 3 would be silly. I'm going to take log 5 of both sides. So if we take log 5 of 3 to the x equals log 5 of 7, now this will use the rule that we just figured out, the previous one. This exponent becomes a multiplier. X times log 5 of 3 is log 5 of 7. And now we just have to solve for x, easy breezy. X is log 5 of 7 divided by log 5 of 3. And then we can sort of state our result. We got that log 3 of 7 is log 5 of 7 over log 5 of 3. And then you can just repeat this in its full generality with letters. The change of base formula is log a of b, and then we're going to switch to c, which was played by 5 in the previous example, so that's log c of, and then what was visually above is still visually above, what was visually lower is still visually lower.